Alright. So today what I want to talk about is mostly just kind of clarifying the notions of stability and the different methods of Lyapunov. We talked a lot about different ways to find Lyapunov functions and all that stuff, but kind of want to clarify what the overarching method is, rather than, and all these other things that we learned about in class are just kind of ways to find these Lyapunov functions which may or may not work. So let's start off with stability, because the homework this week is pretty straightforward, so I'm not going to go too detailed into that. So let's start off with stability. So in E105, E205, we talked about stability of linear system, and we said, we analyzed it in terms of like transfer functions and bounded in, bounded out. So this is kind of different from that. What we're saying, stability, we're talking about stability in the sense of Lyapunov. And really, the Lyapunov theory gives us ways to characterize stability, especially of an equilibrium point. When we do limit cycles, then we got to use the invariant set theorems, which I'll talk about a little bit later. But first, we'll look at stability of equilibrium points. And we can define it as, so I'm going to simplify, I'm going to define it as the stability of the state x equal to 0. If it's at equilibrium somewhere else, you can always modify the equation so that it is at 0. We're saying, so the origin is stable in the sense of Lyapunov. If for any r greater than 0, there exists a small r greater than 0, such that when we start off the system in the smaller r region, the system trajectory is bounded by big R for all t greater or equal to 0. So this is definition 3.3 in Slotine. And Slotine is really a good book for this chapter. It really explains this stuff pretty clearly, I think. So make sure you read the textbook. So if we draw a picture, that's kind of what we did in class. Let's say we have some R. If we move this into 3 dimensions or more, then this becomes some ball, right? What we talked about. And let's say there's a smaller R. So that if we start x in the smaller r, then it's gonna do something, but it'll always be within the big R. So this is kind of Lyapunov stability. We could also have asymptotic stability. So the equilibrium point is asymptotically stable. I'm going to start getting lazy. If it's stable in the sense of Lyapunov, and there exists an R greater than 0 such that X, so if we start off the system inside this R, then our trajectory is going to 0 as time goes to 0. Time goes to infinity. So this is definition 3.4. So it's a stronger statement than the first one. And finally, we have something called exponentially stable. So the equilibrium point is exponentially stable. If there exists two strictly positive numbers we'll call them alpha and lambda. Such that for all t, we have the system trajectory is less than alpha times our initial condition times e to the negative lambda t. So for some ball around the origin. So this is 3.5. So this means that it's exponentially stable if the system is decreasing at a rate that's at least as fast as the exponential function. So it's pretty straightforward. We don't use this one too much, but it's there because the other two don't really give us a measure of how fast things are going to 0. So these are, so all of this stuff is local stability, right? For global stability, well, actually, I don't need to write. So, for global stability, basically our region has to be the entire state space. And we'll go into it more when we talk about the Lyapunov's methods. So, the Lyapunov's first method so this is the thing that we've already seen before, linearization. And it basically says that we have a function x dot equals to some function of x and u, then, and let's say our equilibrium is at 0. Then we can write this as basically linearize it, and then we get some higher order terms that we don't care about. So this becomes our A matrix, so B matrix, and we end up with this kind of thing. So Lyapunov's first method says when we linearize the system, if and we look at our A matrix, if all of the eigenvalues of A are on the left half plane or are negative, then it's asymptotically stable. So we just write that down. So if case 1, if all of the eigenvalues of A do this. Real part of all of the eigenvalues of A are less than 0. Then the equilibrium point is asymptotically stable. If we have any eigenvalue such that the real part of the real part of that eigenvalue is greater than 0, then the equilibrium point is unstable. Now, if we have all of the eigenvalues, let's say most of the eigenvalues of A are on the left half plane, and we have at least one that's on the j omega axis. So if at least one eigenvalue is on the j omega axis. So that means the real part of that eigenvalue is 0, and the other eigenvalues are on the left half plane. So that means for that eigenvalue, the linear part of the system is 0. So that means the higher order terms up here for that mode dominate. And since we linearized it and we kind of ignored all of this stuff, we don't really know what this is doing. So in this case, we can make no conclusions. About the stability. So that's the first method. We've been doing this all quarter, essentially. But just know that it's limited in what it can do. So then we go to the Lyapunov's second method. So this is the direct method. And basically, this is the method where we find a Lyapunov function that's positive definite, and we try to find its derivative that's negative semi-definite, then we can say it's stable. So for local stability, we try to find a V that's positive definite. So a V, right, V of x. So it just means that it's positive everywhere except at the origin, and it's 0 at the origin. So if V is positive definite and V dot is negative semi-definite, this means that we are stable in the sense of Lyapunov. If we have our V dot is strictly negative definite, that means we are asymptotically stable. If our V dot is positive definite, then we're unstable. And for all of these, because it's local stability, we can define for some of them, so V and V dot only have to satisfy these conditions within some region about the equilibrium point, right? And when we choose these, we can basically show what that region is, and it will be stable or unstable within that region. If our V dot is positive semi-definite, then there are some theorems in chapter 4 that tell you something about what you could say about the stability, but it's generally unstable. In that case, we can't really determine a region of instability. We just have to say that that it's unstable, that the equilibrium point is unstable. For global stability, it's pretty much the same thing here, but we require another condition that is V is radially unbounded. So this means that V goes to infinity as x goes to infinity. So, so this is like the norm of x, which is, your x is a vector. It could have many components. If any one of these components go to infinity, your V has to go to infinity. And that prevents situations like where we have, and we get something like this, where, so if this is our contour of V, right, then let's say here we have a locally stable region. We can't say anything about global stability because our V goes to 0 right, as x1 goes to, well, our v doesn't go to infinity, so as x1 goes to infinity. So in this case would be, it wouldn't be radially unbounded. So to make any claims about global stability, we have to choose our v very carefully. So any questions on the Lyapunov? Alright. So again, to reiterate, all of these things are only for equilibrium, stability about an equilibrium point. So it doesn't tell us anything about limit cycles or anything like that. For that, we need the invariant set theorem. So the local invariant set theorem says, say we have our system of the form x psi is f of x. Let v of x be a scalar function of x with continuous first partial derivatives. So note that v of x doesn't have to be positive definite in this case. So we assume that for some L, that our v of x is bounded by L. For some L, we have a region defined by we have a region omega that's bounded, that's defined by v is less than some L. And we require that, we also assume that our v dot is less than or equal to 0 for all x within this region. So these are kind of the assumptions that we're making. So then we say let R be the set of points where v dot is 0. And we let M be the largest invariant set in R. So if we do this, then we can say that for every x in this region omega, so every x in this region will tend to M as t goes to so it seems kind of verbose. What does it actually mean? Well, say we have x1, x2, and we have some region. So our V, let's say the contours of our V is, something like that. It's a scalar function of x1 and x2. And let's say here we have V equal to L, be this contour. So our omega would be everything in here. And let's say that so this theorem is useful when we have cases where our Lyapunov direct method gives us a V dot that's native semi-definite. So we can only say that it's stable in the sense of Lyapunov. We can't say it's asymptotically stable, but you know it's asymptotically stable, and we want to be able to prove that. So if we have the type of system that we're used to, where x1 is position, x2 is velocity, we know that, for instance, it's often the case that you'll get V dot is 0 along the line where x2 is 0. So this would be our R. And M is the largest invariant set in R. So an invariant set is basically if your trajectory goes into the set, it never leaves the set. So if we have a system with x1 and x2, all the trajectories in the system will do something, let's say they're doing something like this, right? Or you got a limit cycle or something. But along this line R, where V dot is 0, right? The trajectory is still moving, so as soon as it enters this set R, it's going to move out of it. So that's not an invariant set. And in that case, you'll find that the only invariant set is, in fact, the origin. So we can say that M, which is the largest invariant set, is just the origin. So then we can say that this will be asymptotically stable, and x of t will tend to the origin as t goes infinity. I think I said limit cycle earlier. That's not the case here. Any questions on that? Yeah.
So could you use this with Krasovsky's theorem?
Yeah. Yes, you can use this whenever you get a V dot that's native semi-definite.
Okay, so if we were to use Krasovsky's theorem, like 3.7, not the general one, but the specific one, and we get the V dot is negative semi-definite, then we could use the invariant set theorem to prove it's negative definite.
So remember the Krasovsky's theorem says the Krasovsky's theorem says that F is A plus A transpose, right? So if F is negative definite, right, then you could then this is stable and V is F transpose F, right?
Mm-hmm.
So so basically, if this condition is true, right, then I think it already says that your system is asymptotically stable.
Right. So I'm asking for if F is negative semi-definite.
Yeah. If F is negative semi-definite, there's nothing you can say.
So you can't use invariant set theorem.
You can't use this Krasovsky's method.
Okay.
Yeah. So this only holds if F is strictly less than 0. If F is negative if F is negative semi-definite, then you'll have to go to the full generalized Krasovsky theorem. Right. And so then if you find, you choose a Q and then you solve for P, and they're both symmetric positive definite, and your F is less than or equal to 0, then your Lyapunov function is FTPF, right? And you're asymptotically stable. Yeah. Okay. So I want to say a little bit about the different methods of finding the Lyapunov functions. So we already touched on some here with the Krasovsky's method. But this pertains more to the homework. So the first is that if we have, so special case for, if we have a linear system, then basically there's a theorem that says for any symmetric positive definite Q, so if the unique solution P of the Lyapunov equation is A transpose P plus PA equals negative Q. So if P is symmetric positive definite, then our system, or our A, is asymptotically stable. So this works for linear systems. And in this case, our P is actually given by and the Lyapunov function for this system will be x transpose px. So for number one, for instance, it's a linear system. We could do this, and what we do is usually pick a Q, say the identity matrix, and we solve for P. And yeah, so it's only a second order system. So theoretically, you could, practically you could solve it by hand. But you could use MATLAB. It's yeah. Be careful when you use Lyapunov because they use A transpose rather than A. So if you don't do this, you'll get the wrong answer. So for linear systems, this is true. For nonlinear systems, generally, you have to follow the other methods for finding Lyapunov functions. For instance, energy. So if you're given x dot plus f of x. So if your equation is of this form, you could try this. And then there's Krasovsky. So I guess in a general nonlinear system in real life, finding a Lyapunov function will be very hard. And you just kind of try whatever you have. But in this course, one of these methods will probably work. So definitely go through the textbook. The textbook has a lot of great examples that explain these things pretty clearly, and that should give you everything you need to do the homework. Yeah. So this week's homework is pretty straightforward, so I don't have that much else to say. Is there any questions? Good? Alright, thanks.